Hi, everybody.
Hello.
Hello, Sam. Hello, Ellie. How are you today?
Okay.
It's a good day. It's a
Okay,
good day
so
and a special webinar.
yeah, it's a very special occasion today. Maybe it's like a gift present for, I don't know, before the spring break or after the spring break, depending of your location. Okay, so I'm going to start sharing um, some slides to make a brief introduction about what is going to happen today, so everybody can be understanding what is happening right now. So, well, welcome to this webinar with the name of Introduction to Couple Inductors by Professor Sam Ben-Yaakov. And before starting the webinar, I would like to just give you a brief introduction about what is Frenetic, that is actually doing this kind of stuff, and then we will jump directly to the webinar from Professor, and we will have a lot of time for questions. So don't worry about that. I'm sure that we will have time to answer any question you have during the webinar. So, what is Frenetic? So, Frenetic is a simulator of magnetics, and we can generate any design or simulate any kind of design, especially for high frequency. But lately, we have introduced a lot of materials in low frequency magnetics. So, if you have a power supply, you will have your transformers, your inductors, and your EMI filters, and all of them could be designed and simulated with Frenetic. So, some of the ways that we see the design of the, let's say, of
Yeah,
a
but
power supply and the magnetics.
start? There is a complaint that there's a problem with the audio by one of the people attending the seminar. Maybe you can
Okay.
look into it.
Anyone can hear me? I mean, is that uh can you
Yeah,
hear me
please,
well?
please use the emojis to. Okay. So now the sound now is well. Maybe it was a problem at the beginning.
Okay. So now it's okay.
Yeah, you
Okay.
can continue.
Thank you. Thank you.
Mm-hmm.
So the way that we see the design of the magnetics is that we have to do first a very good job in the identification of the parameters to make the design. So the construction of the waveforms for different conditions is a key point for us. And that's the reason that we have built the system in the way that we have done, that you will see in a minute. Then we have some design algorithms. This is something very personal. So we have a lot of very expert users that they don't need our design algorithms. They have their own design algorithms. And then finally, the simulation and iteration to get exactly what you need. Our goal is to get 90% of accuracy in all the simulation parameters. And we go to the lab and verify all our models. Currently, the worst scenario that you can find in our technology is in temperature 87% of accuracy after measuring in the lab hundreds of cases. So let me share with you before just launching the webinar. So if you want to get a demonstration or a request for a quotation, this is the QR code that you can use. Here's some our typical use cases that our customers are sharing with us. So just not only design transformers and inductors, but also cases for high isolation situations or very complex designs like CLLC transformers or these kind of technologies. And so basically what I'm saying is that this is just a very easy example of 400 volts, 48 volts, 2 kilowatt case for a resonant converter, where with our technology you can generate the complete design of the application. Let's say calculating the magnetizing, the resonant, everything is automatically done, and then you can design the magnetic. In this case, it was integrated in resonant plus transformer inductor. And if you want to verify what's happening with a planar, so you can do it here. So also you can get a planar case just to verify that would make sense for your application. Here in this case is we can see due to the leakage inductance that is very low, is not going. We will need an additional inductor for the resonance. So probably the compact solution here is going to be much more relevant. And once you are done here, you can jump to the details of our application where you can play with the details of the configuration of the windings. And as I said at the beginning, trying to get different operating conditions and verify the functionality of your component under different conditions. And that's all for my side. Now I'm going to introduce you Professor Ben-Yaakov, who is now actually retired from the university, but he's working as a consultant, primarily in the electrical vehicle area. And the reason that I'm very excited today is because I have been following him for years, and I think that everybody will need to say thank you to him for all the effort he's putting in his YouTube channel for free, because he is sharing all this knowledge for free. We have sponsored him a few videos, but he is not doing this for money. Actually, we just kind of been supporting a few of them, but he continued doing this just for the sake of supporting the community. And there's very few people in the industry that can do that, but especially that can do that in a very good way, because you can really learn. And especially something that also I like from Sam is that he's watching who is saying lies in science, you know? Without more dilation, please follow him in LinkedIn. I mean, LinkedIn and YouTube. And welcome to the webinar. And just looking forward to know more about a couple inductors.
Thank you very much, Kama. And so let me get started here. Is it okay now?
Yes.
Yes.
Okay. Okay. Thank you very much for attending this webinar. I'd like to thank Frenetic and Kama for inviting me to deliver this presentation. And also I'd like to thank Evgeny, who has been helping me to prepare this presentation. Now, the title of this seminar is the Coupled Inductors in Multiphase Boost Converters. And here is a short outline here. We're going to talk about fundamentals of coupled inductors and transformers, interleaved boost, interleaved coupled inductor structure, and then, which I think is the highlight here, combined circuit and magnetic simulation. And throughout this presentation, I'm going to talk a little bit about elements of the magnetic design of a coupled inductor, but obviously due to the shortage of time and the time limit, I will not be able to go deeply into it. Now, as Kema said, we're going to have a question and answer session following the presentation, and there'll be ample time for questions. So let me start off with the question, what is a coupled inductor? We have windings that are sort of coupled in the sense that a flux from one winding is going into the other winding, and then some of the flux escapes, and this is the leakage inductance. Now, what is the difference between coupled inductors and transformer? The difference in the application, not in the structure. They could look the same. The point is that coupled inductors are storing energy. That is, you can have energy coming in one side and also coming in from the other side, same time. On the other hand, when we are talking about transformer, what we mean is that we have an element in which the input power is going out at the same instant to the output, so there's no storage here. So the element here is transparent to the power. So this is the main difference. Now, very quickly, I'll go over the modeling of a coupled inductor. This is the physics of coupled inductor, these two equations. And what they are saying is that we have an inductor, and then we have some flux, the mutual inductance, which represent the flux coming from the other side. And same thing goes for the other output. And we can translate it into an equivalent circuit that looks something like that. When this is a dependent voltage source, and the value here is this M, the mutual inductance, times the current here, and this is vice versa to the other side. For a given frequency, we can use the phasor analysis, and in this case, the derivative becomes omega M, derivative of the I, if it's cosine omega t, and then we end up with this very familiar equivalent circuit or model of a coupled inductor, where M is equal to the coupling coefficient, which is the ratio of the flux going from one to the other side, square root of L1 and L2. And in fact, the way to measure the coupling coefficient is to measure the mutual inductance and then to get the value here from M over the square root of L1, L2. Another way to represent transformers, coupled inductors, is in the engineering domain, I would say, and this is this equivalent circuit for a transformer with leakage. So this could be either a coupled inductor or a transformer. In the coupled inductor, you may have different leakages, but this is an electrical representation. It's not a magnetic representation. I'm going to talk about it a little bit later. In this case, we see here the leakage, we see the magnetization inductance, and for the transfer ratio, we have an ideal transformer, which good coupling, K equal to 1, for the voltage ratio. So this is the very basic, which I think most of you, if not all of you, are very familiar with. So let me go now into the issue of interleaved multiphase converters. Now, in this case, we are talking about, in this presentation, about a boost converter. We have two transistors, two inductors, and they are working together. Now, boosts are used for step-up voltage, power factor correction will typically contain a boost one way or the other. Now, why would we like to have two inductors, two transistors? Well, first of all, the issue of power sharing. Like if the power is high, you would not like to have one inductor, one transistor. You rather distribute the power among various inductors. Also helps to dissipate the power or better thermal conduction. So it is a practice in the power electronic that when you go to higher and higher power to work in parallel. But here, not only that we have a two units, we operate them in a interleaved way. That is, we are not operating them together. There is a delay between one and the other. In the case of two units, it's 180 degrees. And this helps to sort of cancel partially or more or less the ripple. So here I'm showing a simulation of a system like that. Here are the gate drive. This is for duty cycle of 0.5. These are the gate drive. It's about 50% due to the rise and fall time. It's not exactly 50%. But what we see here very clearly that the ripple are in opposite direction, because when one is working, the other one is not. The diode is working, so that we have an opposite polarity of the ripple. So when they are combined at the input, like here, then there is a cancellation here. Here, because it's not exactly 0.5, it's not 0, but it's small ripple. Very important in a boost converter is the ripple at the output, usually very high because of the pulsing here. And also here we have an improvement due to the higher frequency, you might say. So it is improving the ripple And this is one way to operate a multi-phase boost converter. If the duty cycle deviates from 0.5, like 0.8 or 0.2 or 3, then the cancellation is not very good. You see that the inductor current is sort of shifted because of the pulses, the way they are driving the transistors, and then we get a much higher ripple. Still, there is some cancellation, some improvements, but it's not as in the case of 0.5, but still it is better than just a single inductor. Now comes the idea of coupled inductors. The idea is that rather than having two separate inductors, we're going to use inductors which are coupled. And in this case, I'm showing here coupling the same direction. The dots are here. There is another way to do it, alternative way, in which there is a reverse direction of connection. Let me just say that this is better. But I'm showing this just for the sake of then comparing the two and understanding later on why is this reverse connection better, okay? So this is like a reference, you might say. So what we have here is that we have two inductors which are wound on the same body, and so they are coupled with a certain coupling coefficient. And the aim here is to have a smaller size, smaller footprint. Obviously, it's smaller if it's 1 unit, and a smaller size, then it'll be a lower cost. And if it is the same size, then perhaps we can get, or surely we can get better performance. So the idea of coupling is really saving in the operation. Overall, it is like an interleaved multi-phase converter, but the magnetics is, I'd say, smart magnetics, that we have it in a coupled arrangement. Just to get a first impression of what is going on, I've replaced the coupled inductor with the transformer equivalent circuit. These are obviously not coupled, okay? There are dots here which I erased, and this is because of LT Spice putting the dots on the inductor, but they are not coupled here, okay? So this is like an equivalent circuit of a coupled inductor or a transformer, you might say, with the leakage, and in the transformer way of looking at it, rather than mutual inductance, okay? So what we see is the following. If K, the coupling coefficient, is 0, no coupling, then we end up with two inductors. This is the regular case. If K is approaching 1, then we are going to have here actually a transformer, very well coupled. And in fact, here you're going to have a short between these two. So K has to be somewhere in between. And this sort of already shows that this is not a simple thing to design, because there are many, many degrees of freedom here, the value here, the coupling, and the ripple. So this is the problem with actually designing a unit like this. And I hope that this presentation will kind of help those who are interested in actually understanding better the design of a coupled inductor. So to better understand what is going on, I have here now, side by side, two cases. This is a boost interleaved, not coupled. There's no coupling here. The dots, again, are just the LT Spice notation. There's graphics that does not indicate coupling. The coupling is indicated by this directive. Here is coupling between L1 and L2 with the coupling coefficient. This is a parameter of, in this case, 0.5. Okay? So I'm running these side by side just to see the difference between them and how they behave. Now, as it turns out, to get the same ripple in the inductor here and here, and this would be my target, to have the same ripple in the two cases, I can define a different target, but this is what I'm defining here. Then it turns out the inductance that I need here is larger than the original uncoupled case, okay? So this is this coefficient of how much larger is this inductor than this one. And here is a run in which I've already tuned the two to have the same ripple in the inductor. So 1 is the coupled and 1 or 11 is the uncoupled. And here you see that the ripple is the same. This is for 0.3 duty cycle, coupling coefficient of 0.5. And it turns out to get this, you need that the inductance of the coupled inductors of each winding will be twice that of the uncoupled. So you lose here. And of course, then you have to do the summation of losing here, gaining there, and see how much did you actually gain net in this case. This is for 0.3, and for duty cycle of 0.6, again, the target here is to have the same ripple. It turns out that I don't have to change. This is for the same coupling coefficient, same factor, size factor. And we see that the two are in the output, the same ripple. At the input, there is some advantage to the coupled already. You see the green is the one in the coupled, and the ripple at the input is a bit, actually almost half that of the output. So of course I could have decided that I want these ripples to be the same, and this will of course change the situation, and then these ripples will not be exactly the same. Okay, so this is something I can play with. So as I've said, there are two ways to do it. There is the direct connection, same polarity, or reverse polarity. And here now is the reverse polarity. Here are the dots. Everything is the same. This is again the reference, 50 microhenry, two separate inductors compared to this coupled inductor. And here it is. What I see here, again, for a duty cycle of 0.3, coupling coefficient of 0.5, you see that I need only 1.25 larger inductance than in the case of the same polarity of the dots, okay? This reverse case, I can get the same performance in terms of the same ripple with a much smaller inductance. Again, this does not say, this is not one-to-one corresponding to the size, because the size also depends on the flux, which I'm going to talk about. And it's not just the current and the ripple, you have to worry about other things. But you see that on in all, on this comparison, there is a very important difference between the two cases, and the size of the inductance, the value could be much lower than in the case of the same polarity. Okay. Also, we see that the behavior is different, and I'll talk about it a little bit later. 0.6, duty cycle, same story, nothing is changing. In this case, by the way, the ripple at the input is the same for the two cases, and the output also the same thing. Again, due to the interleaving, there is a advantage over one single inductor, of course. So overall, there is an improvement here, and this is just 1 point here. So if I sort of compare the two, I see that for different coupling coefficient, I was working here, I was demonstrating it for the 0.5, I get different values of inductance that I need in the coupled inductor. Now, again, it has to do with what is my target optimum and what I'm looking for, if it is the ripple at the input of the inductor. And again, this is part of the information that is needed, because again, this doesn't say immediately how large will be the element and how exactly I'm going to design it. Now to the question of the shape, which is kind of very interesting, I think. We've seen that in the case of the reverse polarity of the inductors, we have a waveform for the ripple that looks like this. Now, this means that in this portion, for the same inductance, the voltage imposed is much lower because the slope is depending on the voltage imposed on the inductor. And we see here that's almost straight line, while this is not the case here. The question is, why is this so? So let me try to explain it in an intuitive way. You can write tens, if not hundreds of equations here, and then get another equation that you have to solve. And let me try to explain it so that we understand what is really going on here in an intuitive way. So what I did here, I've looked at one particular point, which is the important one. This is actually this section here, in which one transistor is shorted, and here on the other side, the diode is conducting. And these are just arbitrary numbers, just for demonstration. I'm assuming 24 volt at the input and 54 volt at the output. Okay, so the first thing to notice is that we have a voltage drop on these inductors, of course, the difference, and the polarity coincide the same thing for the two inductors. Plus is here and plus is here. And this is in the case of the reverse direction, because the voltages are reversed. And I can represent it as a transformer. Well, this is not a optimum transformer. It's an inductor. It has a lot of inductance, but it is operating as a transformer also. So what we see here is a transformer that on the one side has 30 volt. This is this difference here. On the other side has 24 volt. If the voltages would have been exactly the same, nothing would have happened because it's all balanced. But since we have 24 volts, then we have 6 volt on the leakage inductance, which generate a certain ripple and with a certain slope corresponding to the 6 volt. Now, in the case of the same direction, what we find that now we have a reverse voltage on this winding here. So the difference is the sum here of 30 plus 24, 54. So this is this slope here. And it'll going to be large, while in the case of the point that I'm showing here, when we have the coupled inductor, when one transistor is conducting and the other one is not, then we have this slope. For this case, when the two are, say, the two diodes are conducting, this will be duty cycles, say, smaller than 0.5, then you have a larger voltage, and this is why you have a larger slope here. So this slope is really obtained by this reverse direction, and this is why we prefer this. So now comes the question, how do we get large leakage inductance that we need here? Well, there are two ways to go. One is to sort of separate the windings, okay? And then the distance here, the longer the distance, then the larger will be the leakage inductance, because you have more room for this flux to escape, you might say. And there is actually a nice equation that you can predict the amount of leakage in this case. Or you can put the windings apart, and this again will increase the leakage because you have more flux escaping here, or side by side also. But all these bring about a fairly small amount of coupling, that is a small amount of leakage, that if the coupling coefficient is still fairly high, and here we like to have a small coupling coefficient, a large leakage. And the way to do it is to have a bypass, okay? So we have a structure like this. It can take various configuration or alternative way of doing it. You can have the same gap. You can have different gaps, one small, you can have no gap. Anyhow, the idea is the following. You have one winding, another winding, and then you have a bypass with a small reluctance. I'll talk about it in a second. And by this, more flux is escaping and less flux is getting to the other side. And the coupling coefficient is the ratio between the flux that eventually entered L2 divided by the original flux. So the more flux is, the larger is phi sub 2, the smaller will be the coupling coefficient, and you can adjust it by the gap here and here. And so this is one way to go, and this is a very good way to do that. So now we need some way of understanding or quantizing the magnetic parameter, okay? The simulation that I showed is in a pure electrical. We don't have any notion what is the flux, what is the magnetic flux density, MMF. We don't have any information in this domain, in the domain of the electrical simulation. For that, we need another tool, and this could be very handy, the magnetic reluctance equivalent circuit. And again, I'm sure that most of you know about it and are familiar, if not all of you, but let me go over it very quickly. If I have here say a rod of ferrite with a gap, then the reluctance is defined as the length of the piece, and here is the total ferrite, L1 plus L2, divided by the permeability, total permeability, times the cross-section area. For the gap, the same thing, except the permeability is much smaller because the relative permeability of air is 1. So this number is usually much smaller because of this large number in ferrite, 2,003, 4,000 even, and therefore the reluctance is primarily controlled by the gap if it's not very, very small. So using this concept, we can build an equivalent circuit. It is an electrical circuit, but it is mimicking or emulating the magnetic part. And we see here the 3 reluctances of this body, 3 reluctances. And now we need an interface between the electrical and the magnetic part. And this is done by these dependent sources. Like this dependent source is n, the number of turns, times ddt is the operator of LT5 for derivative. So this is the derivative of the current here. The current represents here the flux, okay? Flux is emulated by current. The reluctance is emulated by resistance. And the MMF is voltage. So by taking the derivative of the current here, I get the back EMF. And so this is the interface, the electrical interface between the electrical part and the magnetic part. So this is very handy. Again, this now gives us information about things like what is the flux in this arm, which is very important in the design consideration. And now I understand that the coupling coefficient can be very easily derived from here, because if I have a flux coming in from this winding, and then it goes this way, and the flux is emulated by a current, then I'm talking about a current divider, okay? And the question is how much of it is going on to the other winding, and this is like a current divider, and by this I can understand what should be the reluctances to get a given coupling coefficient. Now that we have the 2 tools, we can combine them. So rather than having here an inductor, or coupled inductor, I should say, I have this structure, which represents the magnetic part of the coupled inductor plus the two terminals, which are representing the inductor. So these are connected here, okay? These points are connected by this node and by the name, by the designation here, and L22 and N2 is here. And we can run this together and get both the electrical information and the magnetic information at the same time, which is very, very important. And here it is. This is for a duty cycle, which is larger than 0.5. You see the overlapping of the gates. And what I'm showing here is the current here when it is run with this reluctance model and when it is run with the regular inductor, okay? And this is for the reluctance case, and this is for the regular inductor, coupled inductor, and you see that if it is done correctly, it's exactly the same. So now you can ask, okay, if it's the same, why do I need it? I need it because if I run it now like this, I can get information which are not available in the electrical domain, like the flux. For example, I can see what is the flux in a given part of this structure. And if I know what is the flux is related to magnetic flux density times the area, or magnetic flux density is flux over area. So therefore, if I know the flux, I can, for example, just an example, select the cross-section area that I need. Okay, so this is very, very important information in, first of all, understanding what is going on, the losses and the other aspect, and also for the design. And finally, let me say a word about the current sharing. Is there a need for current sharing in this case? Well, you would have thought that since it is coupled, then there is no need, because if it's coupled, then it will sort of divide equally the current, but not so. The coupled effect is on AC only, depends on the IDT, on the derivative of the current. So as far as the DC goes, there's no coupling here. So again, we have a DC circuit, the input, parasitic resistance. This is the parasitic resistance of the inductor, of the transistor. And then we have an average voltage here and here, which is the duty cycle times the output voltage. I'm neglecting the voltage drop of the diode. So if this is not absolutely balanced, everything is the same, like the resistors and the duty cycle, the current will not be the same, the DC current. And so you definitely need current control, current sharing control in this case, if you want the current to be exactly the same. You may tolerate some deviation, and then, of course, you may skip it, but a good practice is to have a controlled current sharing. So what did we see here? I very quickly went over the fundamentals of coupled inductors. They talked about direct and inverse coupling. And what is very important, in my opinion, is the combination of circuit and reluctance simulation that gives you a lot of information. Now, I didn't go into very fine details of the design. And so there is something to do next time. So this brings me to the end here. Thank you very much for your attention. I hope you found it of interest. And as we've said, if you have questions, please write them at the chat part, and I'll try to answer as much as I can. Thank you very much. You are mute, Elizabeth, you are mute.
Thank you. Thank you. Thank you for letting me know. I was letting you know that we have a lot of questions in the questions and answer tab.
Okay.
If you want, we can start reading some of them. I don't know if we are good of time.
Okay, I think I see here the question, so let me try to answer. There's one question, first one by Katalin. How does coupling reduce the size or energy of the total, of the total volume of the coupled inductor compared with two separate inductors? Well, as I've said, due to the fact that you have one body, and then you don't need a very large difference in the inductances, then it boils down to that the total volume for the same performance, let's say for the same ripple, brings you to a saving in the, for the same condition, of course, brings you to a saving of about 30%. That is, the volume will be 30% lower, and also the price will be lower because you have now one unit as compared to two units. And so in general, there is a saving here in terms of the size and price. Now, the question of power is how do you target the design? Like you can have the same power loss as in the case of the uncoupled, or you can have a lower loss, but then, of course, the size will be a little bit larger. I hope this answered this. And then there is a question is, what is the challenge in the design of a coupled inductors, like, for example, a current circulation? Well, as I've said, the challenge is primarily to make sure that the copper losses and core losses are the same, the total, as in the design, or are according to your target. Now, since it is a coupled inductor, it's not that simple and not obvious to get the losses. And what I'm suggesting is to do to be helped by this combined simulation, which will give you information about the fluxes, and which is a cause for the losses, except for the frequency, of course. And then you can optimize the design to get the unit that you need. Now, obviously, it's more complex than the single inductor, but again, the ideas are not too different, except that we don't have a sort of like an AP magic equation that you can use to do the design. It's a little bit more involved. And as I've said, hopefully in next videos, the webinar, whatever, I'll try to cover this too. And then there is a question. Actually, it's not a question, it's more of a comment that it's a good idea to combine the two, and that we can also use it to look at saturation. This is indeed correct. You can design, or you can build a reluctance equivalent circuit that will include a reluctance which mimics the behavior of the hysteresis curve, so that when you have higher, say, magnetic field or a magnetic flux density, you'll see the effect of saturation. So in fact, that you are limited by saturation, you certainly can incorporate it into the model. Now, let me just say that in many modern high-frequency cases, the limitation is not saturation, but rather losses. That is, you are limited by the magnetic flux density due to the loss. Of course, if the current, the DC current is high, you may go into saturation. And all this you can see with this combined simulation of the magnetic and electrical part. And then
Yeah, it seems there are a lot of questions at the same time.
Yeah, just a
Oh,
second. Yeah. Shouldn't the transformer diagram be flipped horizontally into slide where you show the advantage of alternative polarity? I really don't understand the question. I don't understand how flipping something will change anything. So if you have the question, please write to me offline. I'll be more than happy to answer it. And I just don't follow very well the question. So let me go to the next one. Okay, the question is whether to minimize the leakage. No, you should not minimize the leakage, because if you minimize the leakage, then it becomes a transformer. And then it is actually a short between the two sides, because the transformer is shorting the two sides, the two transistors. So you must have leakage. And the problem is that just saying that you need leakage doesn't give you the answer how much. And it turns out that if the leakage is very small, then you have a lot of ripple, and you need the larger side. If the coupling is very low, then you go back to inductors which are uncoupled. So this is the dilemma here in the design, which is, again, as I've said, has many degrees of freedom. And I think that approaching it in the way I did can lead you to the solution, because you can have the reluctance model generic without specifying sizes of cross-section or length, and then optimize it for the reluctance, and then translate the reluctance that you need into the size of the magnetic element. So this, I think, is a good way to go. And then there's the question. Okay, there's a question which I didn't address, which is a good question. Thank you very much for raising it. As it turns out, the optimum operation of the coupled inductors in this case is having two inductors coupled and then other two coupled, not all of them coupled together. There have been some papers showing that it is possible to couple all the inductors. If you have multiphase, that is more than two phases. It turns out that there are many problems there. It's a very, very tough thing to do. And unless one can solve them, I'd say that the more reliable and proven way is to couple every two inductor, not all of them. There are some papers, but I don't know of real systems that have been built this way. I know that there is, in this case, indeed, circulating current among the phases. So therefore, this is an issue that requires very complex control. And again, unless you are in the research area, this is not the way to go, I think. And then there's a question. Okay, so there is a question of how can this waveform can be used for peak current mode. Yes, you can use them for peak current mode. First of all, you can, if it is just for the peak current mode and not for the current balancing, you can look at the input to the whole unit, just to the ripple to the two inductors, and use it, the peak, but you can use each of the units by themselves, because the peak is related, is sort of offset from the average. What you want to control is the average current, and the peak is sort of offset a little bit with half the ripple from the average. So you can actually use it. And so it can be done. There's no obstacle here. And then I have another question. Okay, so there's a question here that if by replacing the normal inductor with coupled inductor size, the then what is the advantage of a coupled inductors if the size of the inductance that you need is larger? I've said it a number of times during the presentation that the inductance by itself does not indicate what is the size, okay? If somebody tells you or asks you, what is the size of 1 microhenry inductor? Well, it could be 1 millimeter, and it could be 10 centimeter, depending on the frequency, depending on the current. So just to look at the inductance does not tell about the size. Size has many other aspects to it, and this is why I think that there's no escape from doing, I think, simulation and looking into all those parameters which are affecting eventually the size. Okay, the size of for example, if a single inductor, and we use the AP approach, the product of the cross-section area of the inductor of the ferrite times the cross-section area of the winding area, depends on B, on the magnetic flux density maximum. It depends on the current, on the RMS current, on the DC current. So there are many aspects there that determine the size rather than just the inductance itself. The fact that the inductance is somewhat larger, so 20% does not say that the unit itself, the physical unit, will be larger, especially since you have 2 units in one package, okay? So let's go farther away. Okay. The question is whether it is possible to use EMI choke as the coupled inductor in the interleaved boost converter. Well, first of all, that's a good question. First of all, indeed, common mode filter is a coupled inductor. Okay, no question about that. But it is not built to store energy. Usually, you don't put a gap in it because the signals that you are filtering are actually the common mode for the two wires together, and therefore there is no net DC flux in the core because the two currents cancel each other. So it is not built for as an inductor in DC to DC converters, for example, a buck or a boost. You would need a gap in order to store the energy because it is not just a transformer and the signals are fairly large and there is a large DC component. Again, in common mode filter, there is no DC component because the wires are run back and forth and the DC cancel each other. Okay, and then we have a question of, yes, the question is about buck. As a matter of fact, it is more popular for the buck converter. And this is because it is popular more in buck converter, I decided to take the boost example, but definitely it is very good for the buck configuration. Very, very good. And then there is a question, how is the interleaved and interwinding capacitance coupled inductor affect the operation? Okay, well, I don't have an answer to that. Clearly, capacitance interwinding capacitance effect. It is primarily the range of frequency that you can operate, the resonant frequency, and it's not too different from any other wound magnetic element. And I think this is the last comment, if I'm okay. So
Yeah,
unless
because
there is a last minute question, I think we managed to answer all the questions. Okay, so again, I thank everybody who came in to attend this seminar. I hope it was useful. You can write to me if there are any questions. I'm more than happy to answer. If you like to elaborate or you need some more information. And then there are some related videos in my YouTube channel about coupled inductor. Not this. This is different from what I've published or posted, but there's still a lot of background information, more about the simulation, more about the reluctance circuit. And so whoever is interested is welcome to watch the videos, the YouTube video. Okay.
thank you,
So
Sam, and of course, a big thank you to you for being with us today. It's been a real pleasure to having you today. I think I speak for everybody, and thanks also everyone who has joined this special webinar. Most of you are asking us about the recording of this webinar. Don't worry, because tomorrow you will receive the recording via email, and Sam, if you want, you also receive the recording just in case you want to upload in your channel.
yes, just a second. I just want to really, first of all, to thank you very much, and just to make clear that make it clear that indeed I've asked originally to have the recording because, well, let's see how it came out. I hope it came out okay, and if it did, then I'm going to upload it to the YouTube channel so that people who have not don't have the contact to Frenetic webinar, etc., will also be able to enjoy it.
Okay, so thank you everybody, and thank you especially to you, Sam, to be here today. Let's connect to the next couple of webinars next week. Thank you.
Okay, thank you very much. Bye bye, everybody.
Bye bye.